Hello. It's a hairdryer, and it's a 1970s Moulinex, styled a bit like a ray gun. It's actually quite a cheap, basic hairdryer, not particularly powerful one. But, amongst other things, it's 100% efficient. Yep, 100% efficient. Cheap, basic hairdryer, but you can't beat it for efficiency. You can't beat this one either. That one's also 100% efficient. Rotel from the 1980s. And as for this 1960s Morphy Richards, well, that one's 100% efficient too. Let's go back in time a bit further. This is one of the very popular British hairdryers that had a very long innings. It's an Ormond, as you can see, in a beautiful Bakelite case. Works. That's actually on cold at the moment. But I probably don't need to tell you how efficient it is as a hairdryer. Converting electricity into heat and pumping it out of the nozzle. Yes, it's pretty well 100% efficient, give or take. Have we got any more? Yes, have a look. There's another one. There you are. That one is actually 1930s. That's a 1930s German dryer. Electrically, it's not the safest appliance I've ever seen. There are quite a few things that could go wrong that would result in a rather serious electric shock from this metal housing. It's not the quietest. I'm not going to demonstrate it now, and it's not the most powerful. But it is nearly 100 years old, so we can forgive it a few things. But guess what? It's nearly 100% efficient. How can that be? How can all these appliances made 40, 50, 60, 70, 80 years ago or more, how can they all be basically as efficient as each other and as efficient as any new machine that you could buy in the shop now? After all, with energy prices as they are, with our concern about energy sustainability, everybody is driving for high efficiency now. But these, I'm claiming, are all basically as good as anything you can buy now. That's not true of all electrical devices. Have a look at these two. This one is a filament lamp. That means it has a tungsten wire inside a vacuum. When current flows through the wire, it gets hot like the heating element in the hairdryer. But it gets so hot that it glows, gives off light, and that's what makes it a light bulb. This one is an LED. Now that uses a completely different technology in which a semiconductor chip passes a current. The current excites the electrons, and as they drop back to their original energy states, they give out light. So there are two very different physical principles, and for that reason, these two are quite different in their efficiency. This one is actually dismally inefficient. It might have been the lighting technology that we relied on for the best part of a century, but actually it's not efficient at all. This still has a way to go, but it is way, way more efficient, maybe 5 times as efficient at creating light from electricity as the old-fashioned filament lamp. But what do we actually mean by efficiency? How do we quantify that? How is it defined? From an engineering point of view, efficiency is the amount of useful work a thing can do compared to the amount of energy that it takes to do it. If you have a machine that takes in 1 kilowatt of power and does half a kilowatt of useful work, with emphasis on the useful there, it's 50% efficient. Half of the energy that you put in is used, half of it is wasted. If the machine does 3/4 of a kilowatt, 750 watts of useful work, then it's 75% efficient. You can't have an efficiency greater than 100% or unity because a machine can only do what you give it the energy to do. The key is to waste as little of it as possible. So we can say mathematically that the efficiency is the output power or useful work done divided by the input power or consumption. You can very often find on the data plate of an appliance how much power it uses. If we look at this hairdryer, we see it's 400 watts. so that's 0.4 of a kilowatt. That's the amount of electricity it consumes. It doesn't tell you how much useful work it does, but we'll come back to that. Looking at the filament light bulb, it's 100 watts. That tells us how much electricity it consumes. Again, it doesn't tell us how much light it produces. So mathematically, we can express efficiency as a ratio of the power in to the power out. How many watts it consumes versus how many watts it delivers. When we looked at the mathematical model of efficiency, I stressed the importance of the ratio of the useful power output over the power input. There's a couple of aspects that govern what is useful power output. Let's have a look at a simple toaster. Yep, it's quite an old-fashioned toaster, but it does what you'd expect. You put the bread in and fold it up, only toasts one side at a time. 2 slices, but only one side of each. The reason I've pulled this out is because you can very clearly see the heating element. Here inside there are 3 strips of mica, which is an insulator, with coils of nichrome heating element wire wrapped around them. And through that nichrome wire passes the electrical current that the toaster uses, and in the process it heats the wire up. And that's the same process that heats up the filament of the light bulb and of course the element inside the hairdryer. And that process itself is 100% efficient. It's the nature of the effect. It's called the Joule effect. It's the process by which electrical current passing through a resistance produces heat. All the electrical energy that goes in comes out as heat, 100%, bar none. But in this toaster, you have the question of whether all the heat that's produced in the element is actually used toasting the bread. It's got some vent slots in the top because heat comes out of the top. Maybe some of that heat comes out without toasting the bread. So now you've got 2 stages in the process. You've got the conversion of electricity into heat and the conversion of heat into useful work done toasting the bread. If either of those 2 stages lacks efficiency, then the overall process of turning electricity into well-cooked toast is inefficient. And in this case, as I say, we've got 1 step nailed. That's the Joule effect heating. That is 100% efficient. But because of the nature of the toaster, the arrangement of the element relative to the bread, you can never make it 100%. Some heat is going to be lost out of the top. You can apply the same logic to a convector heater. That's basically a box with a heating element in. You put it on the floor, you plug it into the wall. The Joule effect turns electricity into heat with 100% efficiency, and then that heat rises up to the ceiling where it's no use to you because what you actually wanted to heat was yourself. So you can have a device that is 100% efficient at converting the source energy into the desired form, but then doesn't fully utilise the converted energy. Some of it gets out, isn't properly applied to the task that you set the machine to do. You could have a washing machine that happily churns the clothes away but doesn't actually get the dirt out because it hasn't taken on enough water, or some other extraneous circumstance makes the overall process inefficient, even though the electrical heating part is 100% efficient. So now we go back to the hairdryer and we have a look at where the energy is going that it's using and where it's coming out, and whether, knowing that the element itself is 100% efficient, whether the overall process is equally efficient. Every hairdryer basically consists of a heating element and a fan to blow air over it. The fan's driven by a motor, so the 2 electrical loads in a hairdryer are the heater and the motor. The heater is by far the largest. The motor might be a matter of 10 or 20 watts, whereas the heater is hundreds, and in a modern hairdryer could be between 1,000 and 2,000 watts. Most heating appliances that give out a significant amount of heat are going to be in the hundreds or thousands of watts. So now we've got it open, we can see it's quite a simple
speed.
So now we've got it open, we can see it's quite a simple beast. There are two main parts. You've got the element and the motor-driven fan. The element is not unlike the element in the toaster or even the light bulb. It's a coil of resistance wire. As the current flows through it, the Joule effect converts the electrical power to heat. We know from theory that part of the process is 100% efficient. The motor, on the other hand, is not 100% efficient. No electric motor is. It converts electrical power to mechanical in turning the shaft to drive the fan, but there is some loss. Just as the current flowing through the heating element dissipates heat because of its resistance, so the motor windings here also have some resistance, and that causes some of the power to be lost as heat. There's also some heat lost in the iron core of the motor and in the bearings and even in the friction between the blades and the air. Normally we might consider that to be loss, so the motor is not doing useful work if it's giving out heat. But the whole point of the hairdryer was to heat the air in the first place, so although in some applications heat lost from a motor is pure wastage, here it's not. It gets used. The air goes in, it gets partially heated by the motor, then most of the heat comes from the heating element, and ultimately two things are delivered from the front. Kinetic energy in the movement of the air, which we need, that's useful work, and heat. Whether it's from the motor, or the friction of the air, or from the heating element, doesn't matter. We've got heat, which is what we wanted in the first place. Here's the Moulin X again. The layout is different, but the principle is the same. We've got a fan at the end. This fan is smaller because it runs faster. It makes the whole thing a bit more compact. We've got the motor, which is technically similar. It's just a slightly different shape, again, because it's higher speed, lower torque. The airflow passes over the motor and then through the element, which is a bit difficult to access, so I haven't taken this part open, and comes out at the front. So we see once again that any waste heat from the motor is collected by the airstream as it passes. So that aspect of the loss, the fraction of the input energy to the motor that is not delivered as useful work in mechanical energy to turn the fan, nonetheless still produces useful work at the output of the hairdryer. So we've established that our ray gun here converts electrical energy into both heat and mechanical energy, which comes out as the kinetic energy in the moving airstream. Is that it, or are there any other forms of energy coming out here that we could count as loss that would make the efficiency less than 100%, or round about 100%? Well, there's noise and vibration. Now obviously these are not desirable effects for a hairdryer. It's got to heat the air and it's got to move the air, but we don't want it to make a noise, we don't want it to vibrate. That's genuinely wasted, and it's worse than that, it's not just wasted, it's a nuisance. So the manufacturers are going to try and minimise that. This one's a little better, it's a bit quieter. Unfortunately you pay for that in the extra size and weight. It's got an induction motor instead of a brush motor, and it makes the whole fan body rather larger. But it is quieter, and you can get quieter still. So maybe this is more efficient because it's not converting as much of the power into noise and vibration. But actually it's a very small amount. If this is giving out a watt of sound and vibration, I would be very surprised. Possibly even not a watt of vibration out of this. It would be very difficult to measure, but I can say with some certainty that the amount of power lost to vibrating the body and to vibrating the air around it, which creates the sound, is really a very small fraction of the total power input. So that's not really a loss term that we're going to be very worried about. It doesn't give out any light, or at least it shouldn't. What about heat that comes out of the hairdryer in a way that isn't useful, that doesn't dry the hair? Well, yes, there is a little bit. The plastic body around the element does dissipate a little bit of radiant heat. It's warm to the touch. It would take 5 minutes, I'm not going to demonstrate it now, it would take 5 minutes to warm up, and that tells us something. There's not that much heat going into the walls because they're being cooled by the airstream. If there was much heat coming out this way, the plastic would melt. This one's probably even better. It's got very little plastic exposed around the element. which is really quite compact. This one here has possibly the greatest surface area of body over the element and possibly has the greatest stray heat loss from the sides. This is a 700 watt dryer, so even if it loses 7 watts of heat in this way, and I don't think it does, but that would still be over 99% efficient. So there we are, all these hairdryers, whether they're made today, 10 years ago, 20 years ago, in the 1980s, 1970s, 1960s, or earlier, whether they've got a centrifugal fan or an axial fan, whether they've got a brush motor or an induction motor, whether they've got a wound metal heating element or a ceramic heating element, doesn't matter. They're all very efficient. All the energy that goes in comes out as useful work. It heats the air, it blows it out of the front. That's what you wanted in the first place. Some are more powerful than others. We saw that one's 700 watts, that one's 400 watts. That's a user choice. You might want a hairdryer that's very powerful. You might want one that has a lower air temperature, uses less power, doesn't scorch your hair. That's a user choice. So long as all the 700 watts comes out at the far end, all the 400 watts comes out at the far end, the power difference is not a factor in the efficiency. They're all very efficient. How about then something else that takes in air at one end, heats it up, and it comes out at the other end? What about that? That's basically the same thing, isn't it? Air goes in at one end, it comes out hotter at the other end, and it does a job of work. In this case it cleans the floor instead of drying your hair, but it's more or less the same, isn't it? Is that 100% efficient? Are all vacuum cleaners 100% efficient? We'll talk about vacuum cleaners in another episode.